Pointwise losses score documents in isolation. ListNet trains on the whole result list, and PyTorch turns that listwise objective into a ranker you can evaluate with NDCG. After this, you'll understand how to assemble a pipeline that learns from query lists and returns a ranking with a quality score. I'm Professor Pi, teaching search and IR with simple Python in search and recommendation. The hard part is getting a short list ordered, so users see the best items first. Pointwise models treat each document on its own and miss how candidates compete with each other. ListNet fixes that by turning graded relevance into a probability distribution across the return set, and PyTorch takes care of optimizing and evaluating that listwise objective. We'll keep the math light. Convert per document grades for a query into a soft top 1 distribution. Teach a ranker to match that distribution. Then measure ranking quality with NDCG at 3. That way, you see the idea end-to-end before scaling it up. We will build a tiny end-to-end PyTorch demo that shows how to create soft targets from graded labels, score documents with a small linear ranker, optimize a listwise cross-entropy objective, and measure NDCG at 3. This keeps the code educational and the math light, so the core idea stays visible before you scale it up. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we show how to turn graded labels into a target distribution for a single query list. This snippet builds the ListNet target distribution for one query list with PyTorch torch.softmax. Listwise learning starts by keeping the documents for a query together instead of flattening them into independent examples. The tensor X holds 4 document feature vectors, and Y holds their graded relevance labels. Torch.softmax y dim equals 0 converts those grades into PY, a top 1 probability distribution over the whole list. The output shows the largest target probability, confirming that the most relevant document receives the most probability mass before training begins. Next, we score that same list and compute the ListNet loss using a tiny linear model. This example scores the query list and computes the ListNet objective with PyTorch nn.Linear and f.cross-entropy. The important shift is that scores is not treated as 4 separate labels. It is reshaped as one distribution over candidate documents. Ranker maps each document feature vector to a scalar, and f.cross-entropy compares those logits with py as soft target probabilities. That gives a compact top 1 cross-entropy loss without handwriting log normalization. The output shows the initial listwise loss, which is the training signal the model will reduce. Scoring one list proves the loss works, but learning needs updates over multiple queries while keeping groups intact. This code trains one PyTorch update over 2 intact query groups using torch.optim SGD. In ranking, mixing documents across unrelated queries would create a false list, so groups keeps each candidate set and relevance vector paired. The generator computes one f.cross-entropy term per query, each with its own torch.softmax label distribution, and sums them before backward. opt.0grad, batch loss.backward, and opt step, then apply one shared model update. The output reports average group loss, showing that the batch is query grouped rather than document flattened. A loss number is fine, but we want to see whether the ordering actually improves for users, so we add a compact ranking metric. This snippet evaluates the current PyTorch ranker with a compact NDCG calculation. Loss is useful for optimization, but IR researchers usually want to see whether the induced ordering improves under a ranking metric. NDCG uses scores.argsort descending true to form the model ranking. rel.argsort descending true for the ideal ranking, and torch.log2 for the position discount. The with torch.nograd block keeps evaluation out of the training graph. The output shows NDCG at 3 for the first query, making the ranking quality visible before the longer baseline run. Finally, we repeat grouped training loops and report mean NDCG across queries for a baseline. This example finishes the tiny PyTorch ListNet baseline with repeated query group training and mean NDCG evaluation. The loop keeps the same structure as the single update. 1 F cross entropy per query list, 1 sum total loss, and 1 optimizer step. Increasing the number of loop iterations gives the linear ranker more chances to align scores with the soft top 1 targets, at the cost of more compute and possible overfitting on tiny data. The final with torch.nograd block evaluates each group and averages the NDCG values. The output shows the trained baseline's mean ranking quality across the toy query groups. You can map this toy flow to a real search problem by treating each user query as a group, extracting per document features like textual match and click signals, and batching updates by query. The same Listwise target creation, grouped loss accumulation, and NDCG evaluation scales to larger datasets once you replace the linear ranker and increase data variety. What we did, we converted graded labels into a soft top 1 distribution and taught a ranker to match that distribution. When to use it? Use ListNet when you care about whole list ordering and your labels are graded per query. One caveat: the top 1 focus simplifies the objective but does not directly optimize all rank metrics. So check NDCG and hold out queries. For a next step, swap the linear ranker for a small 2-layer MLP with a hidden size of 64 and rerun the same group training to see if a bit of nonlinearity improves mean NDCG. If practical IR tutorials help, subscribe and watch the rest of the ranking series.